I hope you are all trying to be happy and healthy and practice social distancing. Again, if if you read my email, what AP has decided to do is cut short the test and make it from a 3-hour test to a 45-minute test. And they have cut off what for us is Chapter 10, which is polars and vectors, and that will not be tested, which is nice. And then for what they call Unit 10, we call Unit 9, which is series, that there's only a couple more topics in series that is going to be on the exam. And we're looking forward to AP saying they're releasing even more details about the test next week. So I think it is fantastic that it only took AP a short amount of time to come up with what seems to be a reasonable and workable plan, and we'll get you ready. Don't worry, the stuff that we have, the stuff that we've done already, you will be ready, and it will all work out. So if you remember my last video, we did some more series building from scratch. And we did a little bit of manipulation as well with series, especially working with derivatives and derivatives of a series and the antiderivatives of a series. Never forget your geometric series, that if you're going to build a series from scratch, if I can do that, see that a over 1 minus r pattern, that's the easiest series of all time to build, and I can find my interval of convergence very easily. We're going to do a couple more pretty famous series today and focus on, again, the things that we believe AP is going to test this year. Remember, none of this work is required. It is purely optional. For some people, they best handle stress by keeping busy and doing a bunch of activities, be it outside, inside, work, reading, exercise. And some people like to, just completely chill out and just absorb being with family, and whatever you need to do is good, right? Whatever you and your family need to do. So I don't want my videos or anything from AP or from the school to stress you out. This is an unusual time. Nobody knows exactly what they're doing. My resources are here just for you if you want them. But please do know that I'm thinking about you. All right, let's do this warm-up. So this is the last video I finished was showing you an AP style question, and this is another one. Notice that AP loves these kind because they don't define a function for you. So even if you know the formula to build a series, it's not really useful here. You actually need to know what it is that you're doing. So, and what the purpose of our series is. So they're telling that you've got some random function f, you don't know what it is, but it has all its derivatives. It's differentiable so that you can find the first, second, and third derivative. They're asking you to write the third order, and remember, third order means you're using the third derivative. That's not the third term. It's not a polynomial with 3 terms. Third order means you've used the third derivative. As soon as they say Taylor, they have to follow the word Taylor at some point with a center. And they did, right there. Now, what can you call a series whose center is 0? What's another name for it? I can say Taylor centered at 0, or I can say what? That's right, MacLaurin. If I say MacLaurin series, I don't have to give you the center because by default, the center is 0. Then notice that they ask you to use the Taylor polynomial. A Taylor polynomial is an approximator. It is not the actual function. Remember, I don't even know what the actual function is. So, whoops, I don't want the highlighter, I want the pen. So, some function I don't know can be approximated by a third order Taylor. Sometimes I call this P, sometimes I call it T for Taylor, third order Taylor polynomial. The Taylor polynomial is exactly equal to, right? The function is the function is approximated by the third order Taylor polynomial, but the third order Taylor polynomial is exactly the function value at the center, technically, and I of course wouldn't normally write this, times x to the 0 over 0 factorial, plus the first derivative evaluated at 0 times x to the first over 1 factorial, plus the second derivative evaluated at 0, x to the second over 2 factorial, plus the third derivative evaluated at the center, which is 0, x cubed over 3 factorial. I don't do dot 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 or an nth term because they ask me only for the third order, which is this. I can clean that up or not. Honestly, it's not really worth my time to clean it up. But the next question asks me to use it. So I cannot plug 0.2 into the function. I don't have the function. But I can plug 0.2 into the approximator. Now I want you to notice 0.2 is pretty darn close to the center. It would be ridiculous to use this third order polynomial to approximate the function at 4 or 2 or even -1, really. You need to stay very, very close, kind of like a little cloud around the center is the only place your approximator should come from. So now I can say f of 0.2 is approximately the third order Taylor polynomial at 0.2, which is exactly -1 plus 7 times 0.2 to the first over 1 factorial plus 5.2 squared over 2 plus 2 times 0.5 cubed over 6. That value is going to be very, very close to whatever this function value is. So let's put this in here. What do I have? -1 plus 7 times 0.2 plus 2.5 0.2 squared plus, what is that? Is that 2 over 6? So that's what, 1/3? So 0.5 cubed divided by 3. Oh, now I forgot what that was. It was 0.9 something, right? So f of 0.2 is approximately the Taylor third order Taylor polynomial at 0.2 which is exactly, I don't know, remember I need 3 places past the decimal. It was 0.94 something, right? You tell me. Now look at the next problem. What's different? Same start, but notice what's true here. I have the original and all the derivatives evaluated at 1. So they're still asking me to write a third order. They say Taylor, so they need to follow that with a center, and there it is. Are you surprised that it's 1? I hope not. And then I hope you're also not surprised to see that what I'm asking you, when I'm asking you to use the Taylor approximator, I'm not asking you to use it at 0.2 because I need to be in a little cloud. This time, if I'm going to use the approximator, my approximator has to be a little cloud around the center. Move a very small distance to the right and left of 1. So 1.2. Delta x is 0.2. So how is this going to change? Still a function I don't know is going to be approximated by a third order Taylor polynomial, which means I have to use the third derivative, and that is exactly equal to -3 right? Now I know we're supposed to have a zero power and a 0 factorial. I'm going to drop that this time. But then watch what happens. I am not going to say 2x to the first. I am going to have 2. I am going to have 1 factorial. But remember, this is a Taylor polynomial with a center not at 0. So I have to have x minus the center to the first plus the derivative evaluated, the second derivative evaluated at the center, x minus that center to the second over 2 factorial plus the third derivative, which is negative, so I'll make that -2. Oops, my battery. X minus 1 to the third power over 3 factorial. So notice that the difference between doing a Taylor with a center at 0, which is the same as a MacLaurin, and the difference of doing a Taylor with a center not at 0. Right? My powers didn't change, right? But my power and my factorial didn't change. Power, factorial, power, factorial. But what did change? Your center has to be there. Right? Think radiate from the center, right? The polynomial, the Taylor polynomial will match the function exactly at the center, and then depending upon how many terms you have, as you radiate to the right and left from the center, the Taylor polynomial will be very close, but not exact. The only exact is the real. And then just like before, this problem is asking me to approximate f of 1.2, which is approximately the third order Taylor polynomial at 1.2, which is exactly now what's going to go here? This is going to be 1.2 to the first, right? 1.2 minus 1 to the first. What happens there? What do you still get in there, though? Aren't I still going to get 0.2? Whoops, this is to the first. Oh, I ran out of room. Right, so you still end up with a 0.2, right? Because that is your distance. Each one of those things is what is your distance from the center, right? This in here is distance from the center. Well, 1.2 is not my distance from the center because my center is 1. The distance from the center is 1.2 minus 1, which is just that 0.2. I'll leave you to actually calculate that. Now, these are the guys that I've been talking about. I introduced them last video. This is Colin, right, the Scotsman. I have a link to a Wikipedia page if you want to read about him. This is Colin MacLaurin. He's always has a center at 0, and this is Brooke Taylor, the Englishman. I don't know if that has an E on the end of it or not. Both of them have horrendous wigs on, in my humble opinion, but I'm sure they looked awesome, and everybody thought they looked awesome in their day, right? But oh my goodness. I mean, this guy almost looks like, right, Mr. Getz's mullet. Can you recognize, now you might be able to recognize their pictures, but can you recognize this series? Who is this series? Is this MacLaurin or is this Taylor? Yes. Can you tell? Center at 0. Right? This is technically x minus 0. X minus 0 to the first. X minus... Now, you could call this a Taylor series. But if you called this, so you would either say this is a MacLaurin series, or you'd have to call it a Taylor series. But if you call it a Taylor series, what do you have to also say? Who's that? That is Taylor, right? And you see, look what I did. Clever. Border blue, border blue. Border on Brooke's picture red, border here red. This is a Taylor series with a center what? Center at A. A being any real number. Ah, who's that? So you might think Taylor Swift when you hear Taylor, but in math class, mathematicians, we think Taylor series. And here's a list of a bunch of Taylor series, most of which you don't need to know. But there are some pretty famous Taylor series, MacLaurin series, that you actually do want to take some time to memorize. Trust me, it'll come in useful. All right, let's do some practice. Given, this time I am going to give you the function. Write the first 4 non-zero terms. Notice I don't say fourth order. I say I want the first 4 non-zero terms. And I also want the nth term. So on a rubric, if this was a question on a long answer AP, there would be points for probably only 2 points for the first 4 non-zero terms, right? You'd get, 1 point for 2 of them being correct, 1 point for 2 of them being correct, and then a third point for the nth term. Don't give them the nth term if they don't ask, but if you're not sure, do the nth term, because there's no penalty for giving them the nth term when they don't ask, but if you forget it, you will lose a point. So I'm going to ask you to write a series for sine x, and I'm going to tell you I want a MacLaurin series. So what does that mean the center is? Good, 0. So here I go. Right, and we did this in the last video. Do you remember sine x, and we came up with the derivatives? Right, the first derivative was cosine x. The second derivative is negative sine x. And the third derivative was negative cosine x, and we saw, hey, we are going to get 0 terms here, aren't we? Every time you put with MacLaurin, right, MacLaurin, where my center is 0, every time my original or my derivative has a sign in it, I'm going to have 0. So notice I have x to the first, then I have an x cubed, an x to the fifth, an x to the seventh. Technically this is over what? And we said the pattern here, with sine being a odd function, you notice that the pattern is the signs alternate, and you start with x to the first, and then the powers in the factorial are odd. So can you write the nth term from that? See if you can do that before I make this yellow box go away. Is that what you came up with? Now, I'm not saying that's the only way, but this term here is my sign alternator, right? And are you okay with that being n? Right? If n is 0, -1 is positive, and my first term is positive. And then I have x to the 2n plus 1. What does that give me? 2n plus 1. Well, when n is 0, that gives me x to the first. And oh look, the power matches the factorial. Right? So this part here is my sign alternator. And this is one way to get odds. There are others, but usually we assume that n is starting with 0 unless you tell us differently. Now what about the interval of convergence? So remember, when we were doing geometric series, what made geometric series so special? If you recognize the geo pattern, you had an infinite sum that was always the first term over 1 minus the common ratio, and that was a convergent series as long as your common ratio, or the absolute value of your common ratio, was less than 1. Geoseries are super special because the interval of convergence is part of the definition. We don't have any such luxury with these other functions that we build from scratch. We don't know what the interval of convergence is, right? So stop. No one has given you this information. Not as a proof, but I am going to just hand you the interval of convergence from sine. I'm going to hint at it with this picture. Here is sine with the center at 0. That function is in black. Now, the blue function is chopping the polynomial after the 5th derivative. The red one is after the 7th. The green one is after the 9th, and so on and so forth. What makes sine? We always knew sine was special. The interval of convergence for sine x is all real numbers. Isn't that freaking nuts? What a gift! What a joy! We will prove this eventually, but for now, you just need to know the interval of convergence. You don't know what it is, but I gave it to you. Or you can't find it, but I gave it to you. The IOC for sine is all real numbers. It's freaking crazy. Now, estimate. Let's use our polynomial to estimate sine of 0.1. Sine of 0.1 is approximately p of 0.1. So that is 0.1 minus 0.1 cubed over 3 factorial plus 0.1 to the 5th over 5 factorial minus 0.1 to the 7th over 7 factorial. Let's get our handy-dandy calculator out. Make sure you're in radian mode and hit 0.1 minus 0.1 cubed divided by 6 plus 0.1 to the 5th divided by 120. Did I go to the 7th? I did, didn't I? Minus 0.1 to the 7th divided by 7 factorial. Now let's hit, what is the calculator approximate sine of 0.1 with? Now this is going to be all very anticlimactic if I've typed something in wrong. Oh no, it's not anticlimactic at all. Boom! Look at that. Where do you freaking think your calculator comes up with sine of 0.1? Right? It's not looking up a table. It's not some little gerbil in there. The calculator is programmed with truncated infinite series. Right? For sine x. That's where it gets it from. It's just plugging it into a polynomial. And look, how many terms is that? 1, 2, 3, 4. Like, oh my gosh, what if I did this? How far off would I be? Let's say I only did 1, 2, 3 terms. 3 terms of the polynomial. Look how close that is to what sine of, right? I mean, my Lanta. Math is beautiful, right? Forgot I typed all this up. Boy, I hate when I do that. Now, what's the difference here? And I get a lot of kids. I don't mean to trap you, but I do mean to make sure you pay attention. Taylor has to be followed with a center, right? So, not 0. This handy-dandy, easy, memorable, right? Easy to memorize formula, sine, odd function, odd powers, odd factorials, alternate signs. Doesn't work as soon as I'm done with MacLaurin. As soon as I take the center off, I have to go back to scratch. Center off of 0, right? If Brooke says, nope, your center's not 0, your center is pi over 3, I'll try to get rid of this. There we go. Right? All this has to go away, and I have to Brooke this up. Right? So what does that mean? Oh, my Lanta. Right? Well, there's my A. What did Brooke tell me my A was? So look at every place I have an A, right? The function evaluated at the center, sine of pi over 3. This really goes away because it's all to the 0. And then I have, right, cosine of pi over 3 is a half, right? 1/2, x minus the center to the first, 1 factorial. Right? All these are the derivatives. Right? The derivatives evaluated at pi over 3. That's what all of these yellows are. But notice that the factorials and the powers stay the same. Right? The only difference is that the derivatives are evaluated at pi over 3, and then you have to have pi over 3 in right? Pi over 3, x minus pi over 3, x minus pi over 3, and all the derivatives were evaluated at pi over 3. So watch out for that Brooke, right? So here's a picture of a couple of the terms of this polynomial, right? But the center is pi over 3. So you can tell, look, I stopped this polynomial at 4. Here's the 4th degree. Do you see it? There's the 4th degree polynomial. And it matches sine of x. Now, the graph of sine x didn't change. The graph of sine x is the graph of sine x, right? Starting here at 0 and, right, going on infinitely. But my polynomial is centered here at pi over 3 and matches sine radiating from pi over 3 really well. Really well. Right? And then not so well here, as I got too far away from the center, right? Obviously, this part of the 4th degree does not match sine. That's the whole idea of shifting the center. Right? It's just where you're radiating out from and where you're going to match from. Oh, who's in the corner? Is it my friend Brooke or my friend Colin? Oh, yay, Colin. I like Colin because, where's my center? Center at 0. So let's write the first 4 terms of the power series. Notice as soon as I say MacLaurin, I don't have to tell you a center. You're supposed to know that. All right, so let's go. We're building this from scratch. So f of x is e to the x. I told you in Algebra 2 you would love e. Didn't I? Didn't I tell you would love e? Because what are all the derivatives? And they want 4 terms, so none of the derivatives are equal to 0. So I just need to go to the third derivative, right? So that is the third. That I could say this is the first 4 terms, but which order would this be? That's right, third order. So now what's the next step? I need to evaluate the function at the center. Oh snap. Right? Aren't they all going to be Aren't they all going to be 1? Right? So what does that mean for my series? So my polynomial approximator, and who am I approximating? E to the x is approximately the function at the center plus the first derivative at the center times x to the first over 1 factorial plus the second derivative, x squared over 2 factorial plus the third derivative, x cubed over 3 factorial. Hold the phone. What does this look like? They didn't ask me for this, but could you write the nth term? I think you could, right? Sorry, I don't want that to show up yet. Actually, what I wanted to do was write this up here in a nicer form, right? Well, this is super nice. How easy is E, right? The Taylor approximator, the MacLaurin series for E, right? Starts with a 1, but then it's x to the first over 1, x squared over 2 factorial, x3 over 3 factorial, x to the fourth over 4 factorial, and so on and so forth, right? So could you write the nth term, even though I didn't ask? I think you could. OMG factorial. Now be careful, because look what I'm going to switch up on you here. Oh, Brooke, you troublemaker. So nothing changes about what my derivatives are. So nothing changes about this line, right? F of x and all its derivative equals e to the x. But what about this line? I'm not evaluating all of those at 0 anymore, right? F of 1 is equal to f prime of 1, which is equal to f double prime of 1, which is equal to f triple prime of 1. And that's all what? What are they all? E to the first. So what does my Taylor polynomial look like? The first term is the function evaluated at the center, plus the next term is the first derivative evaluated at the center, times x minus the center to the first over 1 factorial, plus the second derivative evaluated at the center times x minus the center squared all over 2 factorial, plus the third derivative evaluated at the center times x minus the center cubed over 3 factorial, and so on and so forth. And then I would, if I wanted you to use this polynomial to approximate e to the x centered about 1, I would ask you to approximate 1.1 or 0.9, right? Those values. Whereas if I asked you to use the first polynomial to approximate anything, I would give you values to approximate radiating from 0. I would ask you for 0.1, 0.01, stuff like that. All right. Oh, thank goodness Colin is back. What do you think is going to happen with cosine? I hope you're not too surprised. If cosine is not an odd function, what is cosine? It's an even function, right? The first derivative is negative sine, which is going to be 0. The second derivative is negative cosine, which evaluated at 0 is going to be negative 1, and so on and so forth. So really, this is an x to the 0. This is, remember, this is 1 x to the 0 over 0 factorial, right? And isn't 0 an even number, right? To be even, you just have to be divisible by 2 with no, which means you have no remainder. 0 divided by 2 is 0. I get an integer, no remainder. So for cosine, its polynomial has all the even powers and all the even factorials, still has the signs that alternate. Right? You start with positive, negative, positive, negative. So I still have, in my nth term, I still have negative 1 to the n, which alternates my sign. But then I have, in order to get all my even powers, there's my x2 even powers, and there's even powers factorial. Right? And you do remember what it means to be an even and odd function, right? Sine is odd because it has point symmetry with the origin. Cosine is even because you can fold it across the y-axis and it matches. Crazy, whack, funky, right? What if I asked you to build the function cosine of 2x? You could do it from scratch. You could get the first derivative, but you'd have to take the chain rule, right? The first derivative would be negative 2 sine 2x, right? You could do it. It would just be annoying. But here's a super nice thing about some of your more famous functions. If you remember that this is cosine x's approximator, and you recognize that the only difference between this first function and this second function is that this is cosine x composed with 2x, Well, you know how I build that new function? Now, I do have to remember these terms of cosine, but instead of building from scratch, I'm just going to compose 2x into my polynomial. So look what I did. I did composition. And you know what? I'm not even gonna clean this up. I'm gonna leave it just like this because it's a lot easier to see how to write my nth term. Poof, I'm done. Can you do this next one? That's not a composition, but that is cosine x multiplied by x. So just take your cosine x and do what? Multiply term by term. Take your polynomial cosine and multiply it times x. Now look at what happened here, right? You have to be careful. You kind of have to know what's happening, right? I multiplied 1 by x, and that's where I got x. But notice my cosine usually has, I'm thinking of cosine as having even powers. But because I multiplied everybody by x, right, there's really a 1 there, my powers on top turned to odd powers, but my factorial stayed even. And then, of course, I still have my sign alternator. Right? So using some pretty famous MacLaurin series to manipulate into other series is very useful and often tested. Also, if I do have to build an unfamiliar series from scratch, it wasn't sine and cosine and e, those are pretty famous. It's something different, but then part B says, what is x times that one, right? I'm still going to do this with my known one. So step 1, build your own. Right? Step 1, either build or recognize. Build or remember, a famous one. Build or remember, and then 2, manipulate. Don't build again. And by manipulate, I mean things like composition, right? Multiplication, division, even adding and subtracting. That's added to, don't forget, manipulations you already learned, right? If you have a polynomial, you can always take the derivative of the polynomial of the function, just take the derivative of the polynomial term by term, or the antiderivative of f of x is equal to the antiderivative of the polynomial's terms, right? So lots of things you can do to a series once you build it or once you start with a famous series. So once we have a power series that we know or remember, we can find another or new power series by doing the same thing to the left and right hand side. That's just the golden rule of algebra. So here's a series we built before. This is geometric, remember? This is a over 1 minus r, where r is negative x. And we built this geometric series by finding the derivatives and plugging everything into our formula. Or no, we didn't. We used our a over a is 1 minus r, silly me, right? So we did 1 times negative x to the 0 plus 1 times negative x to the first plus 1 times negative x squared plus 1 times negative x cubed. Remember, if you have geometric, you have no need for the derivatives. You have no need for Brooke or Colin. Suppose I did this first, and now I wanted a new series, but my new series, you say to yourself, this looks like what I just, right? This function is very similar to this one, and the only difference is it gets multiplied by x. So if I say to myself, wait a second, if I just multiply x times the power series I just built, I can multiply all of these times x. To get my new series. Right? Now, this one I could have done my whole a is, right? This one wouldn't have been that challenging to do if I just said, well, hello, a is equal to x and r is still equal to negative x. And I would have gotten the same thing. But it's important for you to recognize, trust me, AP is going to make you manipulate series, even in this new one, or in this shortened AP test. Now, this is a little tricky. Sometimes kids fall into a trap and say, hey, the only difference between a power series somebody built for me and the one they're asking is that the denominator is squared. So I will just square both sides. Yeah, well, that's great, except the right hand is infinite. The right-hand side is infinite. You can't square an infinite polynomial, right? I mean, you can't just square each term, right? You can't, that's not the same. That's like saying x plus y is equal to x squared plus y squared. But this is where one of these other tricks that we've done before comes in. What's the derivative of 1 over 1 minus x? G. The derivative of the function I was given. I was given this one, and I have all of its terms already. They're asking me to find what is basically, right? This is f prime of x, given f of x. Given f of x with its power series, find the derivative. So guess what I'm going to do? I can differentiate term by term. Can't square an infinite sum, but I can differentiate term by term. So the derivative of 1 is 0, derivative of x is 1, and so on and so forth. I differentiated term by term. That infinite series is equal to 1 over x. 1 over 1 minus x squared, but I got it without building it because somebody gave me 1 over 1 minus x first. So, don't build from scratch if you don't have to. And I guess the only exception to this is if it's geometric, because building a geometric series isn't hard, a times r to the n. But any other construction process takes Brooke or Colin, takes derivatives and evaluating derivatives and going term by term. Don't do that if you don't have to. And things, you know, if somebody gives me a polynomial and then asks me for a series with the same polynomial of a composition or a multiplier or a derivative or an antiderivative of, I don't have to rebuild from scratch. Here's another one that we have seen before. I could do derivatives of this, right? I could do derivatives. But how about if I anti-differentiate? Right? If I recognize the antiderivative of ln of 1 over x, right? Isn't this statement true? The antiderivative of 1 over 1 plus x is this. Which means I have a geoseries that's easy to construct, right? I'm not going to avoid construction, but I have easy construction. So I have a over 1 minus r, right? And I just built it, a r to the 0, a r to the first, a r, just like I did before, but that's not the series I want, right? The series I want is the antiderivative of 1 over 1 plus x. So just anti-differentiate term by term. Notice that here, my nth term was an alternator term, and then my powers were just x to the n. Look at what I have here, right? I still have x to the n, but I'm starting with a 1. If I was starting with a 0, and to be honest, AP and math books get a little sloppy with this sometimes, and they expect you to just interpret like, oh, well, that wouldn't be a 0 because then that wouldn't get me my first term. They don't always write that out, so you don't be pressed about it either. Kind of crazy, right? All right. So this lesson was all manipulating series. Oh, I forgot. Since this was a geometric series, I do know the interval of convergence, right? And that's just taking my r from here, right, and saying the absolute value of negative x, which would be x, has to be less than 1, which gives me this interval of convergence. But remember, interval of convergence you can only find on your own from a geoseries. And this one was, even though they asked me about ln of 1 plus x, it came from anti-differentiating a geometric series. In your textbook, right, you've got this list, right? This is a page for, so don't write this down. This is in your textbook, or take a picture of it or something, but I'll tell you the things that are worth memorizing. This looks like a daunting list. I don't bother memorizing this famous MacLaurin series because it is just geometric, right? I have, this is A, right? I don't need to memorize per se this. Here's A and here's R. Same with this one. There's A, this time R is negative x. Very easy to build. Notice since these are both geometric series, I have an interval of convergence. These next ones are famous enough that you need to memorize them. Please trust me, it is worth your time. The series for E, the series for sine, the series for cosine. Also notice, for all three of them, their interval of convergence is infinite. Right? These aren't that hard to memorize. You can build them. You've got the power, pun intended. But e to the x, right? E to the x is just x to the n over n factorial. That's pretty simple. Sine x, the sine, SIGNs alternate. You've got x to odd powers. and odd factorials. For cosine, the sign, SIGNs, alternate, but you've got even powers divided by even factorials. Sine is odd, cosine is even. Please memorize all three of these. It will, I promise, save you time and a lot of questions, or there will be questions that ask you to, given e to the x, given sine x, given cosine x, give me cosine of 2x. Give me e of 1/2 x, the series for that. And all you have to do is plug in. This is another quasi-famous one, but we just did that one. You have to remember this is the one that came from anti-differentiating. Right? Anti-differentiating. This came from one of the and then I don't know why inverse tangent is on there. It's really not that famous, but it's not that hard to memorize. Can you tell? Can you see what it is? There's just you don't have factorials. It looks just like sine x, except it's not. There's no factorials in the denominators. And if you build that from scratch, you would see why that happens. Again, this is page 491 in your book, right? So it's there, but it is these three in particular, and of course how to build a geoseries that you really do have to make sure that you know and practice. So if you want to practice, those book problems on the warm-up slide were there for you to practice if you will, but no problem if you don't. There will be, again, review materials for this when we get a little bit closer to AP time, and my AP review materials are available. We also have our AP Central Classroom site where I'll unlock practice as we go along. I don't want to overwhelm you all at once, so I'll try to piecemeal that after we're done with the last couple of lessons here. So I hope you've enjoyed it, listening to my voice for a while. I do miss you. Take care. Oh, I forgot. Don't forget, these are all centered at 0. Tee hee.